Specific heats of common materials. Overview. Substances do not all heat up or cool down at the same rate. When heat measured in joules is absorbed by substances that do not go through a phase change, the temperature increases. Measuring how fast a substance increases in temperature compared to water gives us this chart, called specific heats of common materials. The chart. The specific heat chart shows how fast a substance heats up compared to liquid water, with water having a value of 4.18 joules per gram centigrade. Any substance that heats up faster than water will have a specific heat value less than 4.18. And any substance that heats up slower than water has a specific heat higher than 4.18. As shown by the specific heats of common materials chart, lead with the lowest specific heat of 0.13 would heat up the fastest. Copper, having a specific heat of 0.38, would heat up slower than lead, but would heat up faster than all substances having a higher specific heat. Granite and basalt, both being rocks, are used to represent land materials. From their respective specific heat values, one can see that land heats up much faster than water, about 5 times as fast. Additional information. If a substance heats up fast, it also cools down fast. As shown by the chart, land not only heats up faster than water, but it also cools down faster than water. This is why the sand on a beach becomes much hotter than the body of water during a summer day, but cools down much faster than water at night. This is also why large bodies of water have major effects on the climate of coastal areas. Water having a large specific heat heats up very slowly and cools very slowly. This property of water causes coastal land areas to have a smaller annual range of temperatures compared to inland cities at the same latitude. Joules is the derived unit of energy in the International System of Units, the SI, or metric system. Question number 1. Liquid water can store more heat energy than an equal amount of any other naturally occurring substance because liquid water. The important thing to remember when answering this question is that specific heat of a substance shows how fast an object heats up or cools down compared to water. The larger the specific heat value of a substance, the more heat it takes to increase its temperature. The important parts of this question are liquid water and store more heat energy. These are the clues about what the correct answer is. Question number 2. How do the rates of warming and cooling of land surfaces compare to the rates of warming and cooling of ocean surfaces? So again, our important clues here are rates of warming and cooling for land surfaces compared to rates of warming and cooling to ocean surfaces. And the thing to remember here is that the larger the specific heat value of a substance, the slower the substance heats up and cools down compared to other substances. When you are looking at your specific heat chart in your reference table on page 1, remember that land is represented by the 2 given rocks in this chart, basalt and granite. Question number 3. The same amount of heat energy is added to equal masses of lead, iron, basalt, and water at room temperature. Assuming no phase change takes place, which substance will have the smallest change in temperature? So we have important stuff here. We have the same amount of heat energy being added to equal masses, so they're all the same, of lead, iron, basalt, and water, they're starting off at the same temperature. No phase change takes place, and it's asking which substance is going to have the smallest change in temperature. So we're looking for which substance, lead, iron, basalt, or water, will have the smallest change in temperature. The important thing to remember for this question is that the greater the specific heat value is for a substance, the slower it will take for it to undergo a temperature change. So the greater the specific heat value, the larger the number for a substance, the slower it will undergo a change, the longer it will take to change temperature. So what you need to ask yourself is, if you're going to have a small change, will it take a long time to change temperature, or will it take a short time to change temperature? Question number 4. 5-gram samples of granite, basalt, iron, and copper at room temperature are placed in a beaker of boiling water. Which sample would reach a temperature of 60 degrees first? So important stuff here. We have the same mass for each one of these samples, same mass for granite, basalt, iron, and copper. They're starting off at the same temperature. They're starting off at room temperature, and they're placed in a beaker of boiling water. And we know water boils at about 100 degrees Celsius. And it's asking which sample would reach a temperature of 60 degrees first. This is the important part. It's asking which one's going to reach 60 degrees first. That means that it is going to heat up the quickest. Remember that all of the given substances have the same mass and are at the same initial temperature. Once they are placed in the boiling water, the substance that has a lower specific heat will increase temperature the fastest. Question number 5. When the sun sets, which material would cool down the fastest, assuming they all have the same mass and initial temperature? So we're looking for which material is going to cool the fastest. Remember that something that heats up quickly also cools down quickly. So you are looking for something with a low specific heat. Question 6. Large oceans moderate the climatic temperatures of surrounding coastal land areas because the temperature of ocean water changes. So when we read this, moderates means to even out. It means that it's making it more equal. So it moderates the temperatures of surrounding coastal land areas because the temperature of ocean water changes. What you need to remember is what the specific heat of water is. If you look at your specific heat chart, you will notice that water has a high specific heat. So what does that mean about how quickly or slowly it will cool down or heat up? Compared to the climate conditions of dry inland locations, the climate conditions of locations influenced by a nearby ocean generally result in. So we are comparing land to water climates. What we need to remember is the specific heat of land, which is lower, which means that it will heat up and cool down quickly compared to water, where it will heat up and cool down slowly. So if we know land's going to heat up quickly and cool down quickly, what does that mean in the summer? If land heats up quickly in the summer, we should expect that we are going to have warm summers. And if it cools down quickly in the winter, we should expect that we have cold winters with a large temperature range. So if we're talking about ocean climates, or locations near the ocean, we should expect the opposite effect because the specific heat of water is so much higher that it causes it to heat up and cool down slowly. Properties of water. Overview. When ice absorbs heat, measured in joules, its temperature will increase until it reaches 0 degrees Celsius. At this temperature, it undergoes the phase change of melting. Now, as in all phase changes, the temperature remains the same until the phase change is completed. When the ice has completely melted and heat is still being applied, the temperature of the water will increase as the water absorbs heat energy. So as water is melting, it is absorbing heat energy. After it has melted, it will continue to absorb heat energy. At 100 degrees Celsius, at sea level, the water has reached its boiling points and begins to boil. It will stay at this temperature during this phase change while continuing to absorb heat. During the phase changes of condensation and freezing, heat is released. It seems strange that as water freezes, it releases heat. But it is exactly what happens. In fact, within a hurricane, a tremendous amount of heat is released when water vapor condenses. This is a major source of energy for the hurricane. The chart. For ice to melt from a solid to a liquid, it must absorb heat. The chart shows that 334 joules are absorbed or gained for every gram of ice that melts. For water to freeze, or going from a liquid to solid, it must release or lose 334 joules for every gram of water that freezes. Notice that in these two phase changes, the number of joules are the same, but the difference is whether the energy is being absorbed or being released. Both of these phase changes occur at 0 degrees Celsius, and the temperature remains the same while the phase change is occurring. In vaporization, or boiling or evaporation, a liquid changes into a gas. For vaporization of 1 gram of water, the chart shows that 2,260 joules are absorbed. When condensation occurs, which is a gas to a liquid, each gram of water vapor releases 2,260 joules as it changes back into liquid water. Both of the phase changes occur at 100 degrees Celsius, and the temperature remains the same while the phase change is occurring. The density value of water is 1 gram per milliliter. As shown on the chart, this occurs at 3.98 degrees Celsius, which can be rounded up to 4 degrees Celsius. When water warms from this temperature, its density slightly decreases. This is why warm water rises, being displaced upward by the sinking, cooler, denser water. Additional information. Any substance that has a density less than 1 gram per cubic centimeters will float in water, while a substance with a density more than 1 gram per cubic centimeter will sink when placed in water. Ice floats in water since its density is very close to 0.9 grams per cubic centimeters, which is less than 1 gram per cubic centimeter. Question number 1. Which phase change requires water to gain 2,260 joules per gram? So our clues here, phase change, so we know we're talking about properties of water, and gain 2,260 joules per gram. So if you look at the chart, on the first page of your reference table, you will see that you have 4 choices. You have melting, freezing, vaporization, and condensing. And you need to pick the one which is gaining or absorbing 2,260 joules per gram. Question number 2. During which phase change of water is the most energy released into the environment? So our clues here is phase change, so we know that we're looking at properties of water, and it says released and most energy. So we're looking for the largest number which is released into the environment. So again, taking a look at your reference table, you have 4 choices. Look for the largest number that is being released. Question number 3. How many joules are required to evaporate 1 gram of boiling water? So you need to take a look at your chart. It's asking you how many joules are required to evaporate 1 gram of boiling water. It'll be a fairly simple and straightforward question. Occasionally they will ask you more than 1 gram, in which case you would have to multiply that number, which is given on the table, by whatever number of grams they give you in the question. Question number 4. Which statement best explains why water in a glass becomes colder when ice cubes are added? So the important thing to remember with this statement is something that wasn't in the reading before, and that is the idea of sources and sinks. Remember, the energy always flows from sources to sinks. And so what you need to decide when looking at this is whether or not the water in the glass is the source of energy or is a sink of energy. Remember that when ice is added to water, the ice begins to melt. So when you are melting, are you absorbing heat or are you releasing heat? That is another way to think about it as you are looking at the chart on the first page of the reference table. Question number 5. What is the total number of joules required to melt 100 grams of ice at 0 degrees to liquid water at 0 degrees? So again, we're talking about 0 degrees to 0 degrees. That's no temperature change. That means that we're talking about a phase change. Our phase change is melting, and we are melting 100 grams. Now remember, before on one of the other questions I had stated that sometimes they will give you the same kind of question, but they will give you a mass. So in this instance, you need to multiply the energy that goes into melting the ice by 100 grams in order to find out what that total number of joules are that are required. Question number 6. The cartoon below presents a humorous look at science, and unfortunately they don't really use a lot of comic strips anymore on the Regents exam, and this happens to be one of my absolute favorite comic strips, Calvin and Hobbes. Calvin says to his father, "Why does ice float?" His father states, "Because it's cold. Ice wants to get warm, so it goes to the top of liquids in order to be nearer to the sun." Calvin, "Is that true?" His father, "Look it up and find out." Calvin, "I should have just looked stuff up in the first place." And his father states, "You can learn a lot talking to me." So the correct explanation of why ice floats is that compared to liquid water, solid ice is. And so you have to remember one of the statements that was made at the very end of the reading at the beginning of this review packet about ice. That wraps up this review, properties of water and of the specific heats of common materials. Make sure that you are prepared on Thursday. We're going to go over the answers, and then on Friday we'll have a quiz. So if you have any questions, be ready on Thursday to ask the questions for the quiz on Friday.